what is, the unit that we're going to talk about is linear systems. Okay, linear systems. What is a system of equations? A system of equations in general is a set. Oh, there we go. Of two or more equations and two or more variables. Okay, so we can actually have systems of linear equations, systems of quadratic equations. There's lots of different equations that you can involve in a system. But in this course, we're just going to stick to linear. So what does that mean? All of the equations that we're going to look at will be a linear relation, which is what we looked at last unit. Okay? The solution is the value of each variable that satisfies both equations in the system. I should say all equations, because sometimes you can have more than that. Okay, so in this course, by the way, we're only going to look at systems of linear equations in two variables. Okay, the rule of thumb is that you have to have the same number of equations as variables to solve the system. If you have 3 variables and 2 equations, you don't have enough information. Okay? Essentially, what you're going to have is 2 unknowns and 2 constraints, which is exactly what we just saw with that Chips and Reese's situation, right? The 2 constraints were the 2 transactions, where we had different numbers of each item totaling a certain amount. And that certain amount was the constraint. Okay? Now, we're going to look at 3 strategies to solve these. Today, we'll look at solving them graphically. And then starting tomorrow and into next week, we're going to look at 2 different algebraic techniques. But that's basically what we're going to be doing for the whole unit, working with these types of equations, these sets of equations, and just looking at different ways to solve them. Okay? All right, let's start with graphically. So we have these 2 linear equations that make up a system that are graphed on this coordinate plane. What do you guys think is the solution? Yes?
The intercept.
Yeah, the intersection point, right? Because that's the point that lies on both lines. And if a point lies on a line, then the value of x and the value of y of that point, when you plug it into the equation, should make the left side equal to the right side. Okay? So we're looking for the one that lies on both lines, which is the intersection point. Okay? So that, in this case, happens to be the point -2, 3. Okay? Now, what we're going to do is let's sort of review what we did last unit and come up with the equations for each of these graphs. Right? So these are linear equations. What pieces of information do we need to come up with an equation for those lines? Yeah?
Either the slope and the y-intercept, or the slope and a point.
Yeah. Either the slope and y-intercept or the slope and a point. And we actually have the y-intercepts very clearly on both of these lines. So we can go with that. But let's look at the red line first. Okay. What is the slope of this line? If I'm going from this point to this point, let's say. I'm going up, how many?
2.
Up 1 and right 1. So that slope is 1. And then what's the y-intercept?
5.
5. 1x plus 5. Or you could just write x plus 5. Okay, and then for the blue line, okay, let's figure out the slope of this line. Let's say we're going from here to here. I got to go down 1, right 1. So down is a negative slope, okay?
All clear, all clear, all clear.
And then the y-intercept is 1. Okay, so that makes up this system. All right, now explain why these coordinates are the solution.
If there's anybody in a room that has not been released, can you call the main office, 403-243-8880, extension 0, and we'll be able to send the police your way. If you haven't been released from a room, call the main office.
Okay, so why does the coordinate -2, 3 solve this system? Why is it the solution to this system? Yes?
Because it has to work for both equations, and that's the only point that is on both lines.
Yep, so it is the point of intersection. So that's true, it falls on both lines. We can also show that when we plug -2 in for x and 3 in for y, the left side is equal to the right side, okay? So there are sort of 2 explanations here. Falls on both lines. And also, if we verify, we actually have to verify all equations in the system. So we can verify by subbing in, right? So the one equation was y equals 1x, or x plus 5. And the other equation was y equals -x plus 1. And we're verifying the point -2, 3. Okay, so if we plug in a 3 for y and a -2 in for x, we want to make sure that each column is equal to one another, right? So the left column is just 3, -2 plus 5 is 3. So this is good because the left side equals the right side. Okay, and then in this scenario, again, y is 3. X, be careful here, it's -x. And x itself is negative. So it's -2 plus 1. And that comes to 2 plus 1, which is 3. And now we have the left side equaling the right side again. Okay, so these are various ways to verify. If you are asked to verify, though, typically this is what we want to see. Plug the solution into both equations. Make sure that they both check out. Okay? You can write a solution as a coordinate point. You can say the solution to this system is -2, 3 in brackets. Okay? All right. Now, how do we solve these if we don't have a graph? Well, this basically means we have to just review graphing a little bit, which is what we did last unit. Okay, so we're now going to look at this system here. 2x plus y equals 3, and 6x minus 2y equals 4. And I have here 3 different strategies that you can use to graph. I kind of don't want to do the table of values one, though, because it's super inefficient. And we have now learned other ways to graph that are much faster, right? So the idea with the table of values, you plug in a bunch of x values, and then you use the equation to figure out the y values, and you plot those points, okay? We've now learned how to graph either using intercepts or to put the equation into slope-intercept form. So I'm going to skip this one because this is not efficient. Although you could do it. Okay, there's nothing wrong with it. It just takes a really long time. And we're going to look at this one instead. Okay? So if we're looking at graphing the intercepts, then we need to remember that at each intercept, one of the coordinates is 0. So if I'm looking at this equation, 2x plus y equals 3, I can just put a 0 in for each variable and then try and solve. Okay, so if x equals 0, I can just cover up the 2x because that's going to make 0, and I end up with y equals 3. And if y equals 0, I can cover up the y, and I'm solving the equation 2x equals 3. Well, if 2x equals 3, that's this guy, what's x? 1.5, yeah. 3 over 2 or 1.5. Okay, then I'm going to do the same thing here. Okay, so if x equals 0, I'm solving the equation negative 2y equals 4. So this guy, what would y be? Not 2, almost. Negative 2, because we got to divide by negative 2. Okay, and then if I'm solving for the x-intercept, this equals 0. So here I'm going to have 6x equals 4. So how would I get the x-intercept rather? Yeah, so I need to do what? Divide by 6, yeah. Right, and then 4 over 6 is 2/3. Okay, so I can graph those points. So the one is the point, ugh. This guy, I've got 0, 3, and then 1.50, that's right here. And then I'll just connect them. Okay, there's the one line. And then for the second one, I've got 0, negative 2. That's down here. And 2/3, 0. So that's kind of like right here. And I can see a point of intersection right there. Okay, and that's the point 1, 1. Okay. You could also graph this using slope-intercept form, which just means we have to do a little bit of work to isolate each variable. But that should be okay, right? So if I do this guy, 2x plus y equals 3, how do I isolate y in that equation? Yes?
Minus 2x.
Yeah, we subtract 2x. We start by trying to get, what's minus 2x? The y term by itself. And then sometimes we have to do more on top of that. In this case, it's done. Okay? And then for the other equation, how can I isolate y? Yeah, I can first isolate the y term. So I'll take away 6x, and I end up with negative 2y equals negative 6x plus 4. And then, what do I need to do? Divide by negative 2, right. Okay, and then simplify. So this becomes y. Negative 6 over negative 2 is 3. And then 4 over negative 2 is minus 2. Okay, and then I can graph those, right? So I'm going to start the first one by plotting the y-intercept, which is at 3. And I can go down to right 1, because the slope is negative 2. That's like negative 2 over 1. Down to right 1, down to right 1, down to right 1. Or you could go up and left. Okay, and there is this one line. I have to kind of do it head on, or else I mess it up if I try and write from the side. There we go. Okay, and then the other one is 3x minus 2. So we're going to start at the y-intercept of negative 2 and go up 3, right 1. It's 3 over 1, right? So up 3, right 1. There's the point of intersection, up 3, right 1. Okay, so there's the next line. And that, of course, is the same point, 1, 1. So that is the solution to this system. Okay? Questions with that so far? All right, so I'm going to go to the next page, And there are 2 examples on this page. I want you to try at least one of them and verify it. If you have time, you can try them both. Unit is about solving application questions, which is similar to what we did with that first problem with the candy and chips, with the Reese's and Doritos. And so we are going to practice that almost every day. And what we're going to do is use sort of the strategy of the day to solve the problem. So today we're solving everything graphically. Okay, tomorrow we're going to use a method called substitution. And next week, we'll use a method called elimination. But these application problems, no matter what the method, a lot of the steps are the same. Okay? With this first one, we'll read through it, but you actually don't have to come up with these equations for this question. They're given to you. Okay, so we're going to talk about a little bit about why they make sense, why they model the situation, and then we're going to do an example where we actually have to come up with the equations ourselves. Okay, so here's the situation. One plane left Regina at noon to travel 1,400 miles to Ottawa at an average speed of 400 miles per hour. Another plane left Ottawa at the same time to travel to Regina at an average speed of 350 miles per hour. A linear system that models this situation is this. Okay? And D in these equations represents the distance in miles from Ottawa. T is the time in hours since the planes took off. Okay, so before we even start to talk about what we're being asked to do, let's just actually figure out what's going on and why these equations make sense. Okay, so what we have is we've got 2 cities, Regina and Ottawa. And we've got, and oh, by the way, what's the distance between them? How far are they apart? 1,400 miles, yeah. Okay, and we have a plane that is leaving Regina. That's my plane, at noon, and it's going 400 miles per hour. And then at the exact same time, we've got a plane leaving Ottawa. Wouldn't be noon in Ottawa, but because of the time change, this is 350 miles per hour. Okay? And in the system, we've got 2 variables, distance and time. Time is how much time has passed since the planes took off. And distance is how far each plane is from Ottawa. Okay? So let's make sure that we understand why these make sense. Okay? D equals 1,400 minus 400t. The 400 means it's probably looking at this plane, right? So at the start, it's 1,400 miles away, and then every hour that passes, it gets 400 miles closer. So the distance for this plane keeps decreasing. Starts 1,400 miles away, and then it keeps getting smaller and smaller until eventually it arrives in Ottawa. Whereas for this equation, D equals 350t, that looks at this plane, right? At the start, the distance from Ottawa is 0, and then it keeps increasing by 350 miles per hour. Okay? I'm just getting distracted. Okay, thanks. All right, so graph the system. Now, I put in brackets here, do it using a graphing calculator. We're going to actually do this and then talk about why it makes sense to use technology to do this. So actually, I'm going to just reset this because I just did it with my last class. And I want to kind of start from scratch with you guys. So I'll do the same thing here. F5, that's a little review for you guys on clearing calculators. Okay, so if you have a Casio, to graph, you are going to go to Menu, and you guys have done this before, and select Graph. So here it is. And then we are going to enter in the two equations. So the one equation was 1400 minus 400x. Remember, you have to use this as your x button. And the second one was 350x. We have to use x and y on the calculators, even though the problem uses the variables d and t. Okay? So now if I hit enter, I can draw this thing. And what you can see is that I really don't see very much. And if I were to do this on the TI, I'm going to quickly do that as well. I'm going to go to y equals 1400 minus 400x and 350x. Okay, I don't see much there either. Barely see anything. Why? Yes?
Your window setting.
Yes. So this is the hard part to solving these applications graphically. Okay. Is you really have to put yourself in the problem, understand what each variable means, so you can find appropriate window settings, okay? X replaces t. That's time. Think about a flight from Regina to Ottawa. Approximately how long would that take? Think even from Calgary to Ottawa or Toronto. Well, so how many hours roughly? Yeah?
Like 4-ish.
4 or 5, yeah, sure. So that's our X, right? So I'm going to go to window here, and I'm also going to go to window here. And I'm going to set my X min, the minimum amount of time is 0. And the max amount of time, let's overshoot a little bit, I'll make it 6. And the scale is still 1. Okay? Now y represents the distance, okay, from Ottawa. What's the minimum distance from Ottawa? 0. And the maximum? 1400. So I will maybe make this 1500. And I'm going to make my scale 100 so that I don't have 1500 ticks along the y-axis. And then I'm going to redraw that, and I have a really nice graph now. Okay, so I'll do that on the TI as well. So this was 0, 6, 1, and then this was 0, 1500, and 100.
For some reason, mine is graphing 3 lines, even though I only have 2 equations.
Okay, I'll come look at that in a minute, okay? All right, and there we have it. Now, we also need to find the intersection points. So on the Casio, how do you find everything out on the Casio? What button do you have to press? G-solve, yeah. So G-solve, and then which of these do you think we're going to select? Intersect, yes, F5, just gives us the intersection point. So that's 1.8666666, 653.333333, etc. Repeating, okay? On the TI, where are we able to do all the stuff? Yes.
Under the calc menu, which is second trace.
Second trace, exactly. And we are going to select which number? 5, yeah. Okay, now on this one, you're asked to put the cursor close to the intersection point on the first curve and on the second curve. Okay, so I'm going to hit enter and then enter again. And then do I want it to guess? Yes, I do. And we get the same intersection point. Okay, now the reason why it's better to do this using technology than by hand is because the scale is so large. And so if we're graphing by hand, we can't have 1,500 ticks if we're doing it on a piece of paper. And so we will have a rough idea of where the intersection point is, but we won't be able to get it exact. It would be an approximation. Okay? All right, so I also want to talk to you a little bit about how do we show this? How do we show our work when we're graphing using a calculator? Whoops. Okay, so because when you are asked using technology to graph something, you do have to show people what you've done. And what you want to do is be able allow the other person who's reading it to recreate exactly what you did on the technology. And there is a specific format that we in general as a math population or community follow, okay? And it looks like this, okay? So what you're gonna do is make a square, or a rectangle actually, and this represents the screen of your calculator. So on here, you are going to put in what you see. And what we saw was something like this. Okay, and this intersection point was 1.86 repeating and 653.3 repeating. Okay, and then we also, in order for someone else to be able to create this, they need to know the equations we were working with. So we're going to enter those up here. Y1 is 1400 minus 400x, and y2 is 350x. Okay, so that's important information for people to know. And then there's one other thing that we have to tell people so that they could recreate this exact same picture. The window settings, right? So we put those in 2 square brackets underneath, one for x and one for y. And the format is you're going to put 3 numbers in here, x min, x max, x scale. And to be honest, I don't know why we have to put the scale in, but this is the format that the diploma exam follows. When I was in high school, we didn't have to include the scale. Okay? So that, in this case, was 0, 6, 1. And then this is the same thing, but for y. So 0, 1500, 100. Okay? So that's what I would like to see if you are graphing. This is how you show your work using technology. All right, and then right before we finish for the day, let's actually answer the question, which is, when do the planes pass each other? And how far are they from Ottawa? Okay, well, which variable refers to time? X, yeah, so they will pass each other, right, when 1.86 repeating hours after noon. Afternoon, I think it was Regina time, right? Well, we don't usually talk about time as like 1.87 hours afternoon. We usually talk about like hours and minutes. So how would we convert this? I mean, 1 hour afternoon is 1 p.m. But what about the 0.86 hours, 0.86 repeating hours afternoon? How do we convert that to minutes? What do you think? Yeah?
Now, possibly, would you multiply it by 60?
Yes, exactly. This is essentially like, if we round to the nearest tenth, 87% of an hour. And an hour is 60 minutes, right? So this part is 86 point, let's say 67 to round, percent of 60 minutes, because 60 minutes is 1 hour. Okay, so when we're working with percentages and doing calculations with them, this type of problem, like a percent of question, the word of means multiply, and then the percent has to be in decimal form. So 0.8667 times 60, and that is, I don't know, what is it? It's about 52. Okay, so we could say 1:52 p.m. Regina time. Okay, and then what about the distance from Ottawa? What's the distance from Ottawa? Yes.
653.3 repeating kilometers.
Yes, so this is the distance, right? How far are they from Ottawa? That's 653.3 miles, right? The only thing you have to be careful of here is I could also ask how far they are from
A
Regina.
couple of announcements before the lunch bell goes.
Okay?
The art
We'll stop
gallery,
there.
which is just down the English hallway from the main doors. They're going